So hello and welcome student to today's lecture, and this is course number MA412 linear algebra, and lecture number 30. Okay, now recall that we are discussing about normal operators in our last lecture. So we defined the normal operators are those operators on inner product space such that the operator commutes with its adjoint. So the adjoint exists and they commute with the adjoint. Okay. Then we call this normal operator, right? And then we prove that. Okay, so before that we use something called source theorem to prove that if that monic characteristic polynomial split for some linear operator on finite dimensional vector space, inner product space, then you have a basis whose elements are orthonormal. So this is orthonormal basis such that the matrix implementation of that operator becomes upper triangle, right? And in particular, with this normal operator on complex finite dimensional vector space, inner product space, then it is actually equivalent statement that is normal if and only if you have a basis or orthonormal basis of eigenvectors, and that we already proved. Okay, so obviously maybe note that. So maybe let me just recall the theorem again. So if so your V is finite dimensional complex inner product space, that is important, very complex inner product space, then T normal is if and only there exists a basis or orthonormal basis, orthonormal basis of eigenvectors of T. Okay, so that is important. So recall that I used two facts. One is this finite dimensional, one is complex inner product space. So so I will give maybe some example why these two are important. But before that, let us do some properties of normal operators, and then I will come back to the examples. So so suppose what is given to me that I have a inner product space and I have a normal operator. So this is given to me. So T belongs to LV is normal. This is given to me, and then it has many properties. So the first property is that the norm of T of x for any vector x is equal to norm star of T of x is true for all x belongs to V. Okay, and the proof is simple, or rather not so difficult. So how do you prove? So you start with the definition. You know that norm of x whole square, it is actually in a product of tx, right? And you can use the property of normal operators, and then you will have t star of T of x comma x. Okay, and then you know that because T is normal, then you can write it down as T of T star of x comma x as T star equal to T star T. So they commute to each other, right? so you can write it down. And hence again now you are going to use the property of inner product again, and that gives you that it is t star of x comma t star of x. Okay, now which is nothing but norm of t star x whole square. Okay, and hence that proves that norm of tx equal to norm of t star of x for all x belongs to D. Okay, the norm is equal. Okay, so if you have non operator, that means the t star also exists and they commute to each other. Not only that, the norm of image of t and t star of any vector is always same. Okay, these important things. Second important property is that this t minus this linear operators with t with ci is always normal for any c belongs to that field. The field is anything. Okay, for any field this is true. Okay, and the proof is what? The proof is also not so difficult. So this is normal, means you need to check that these commutes with this that complex conjugate, or rather yes, you can say complex conjugate. So by by property of star, you can write it down this by t star and ci whole star, right? And then you can use the property of star, that adjoint, and you know that constant will come by the bar here, c bar, and I star equal to I, right? So this is because I star equal to identity adjoint of identity itself. Now because normality means t star commutes, so now you can easily check that this is t star minus c bar t minus c t star, and then plus c bar I. So c bar I means more c whole square, right? So this is, we can write it down as t star comes to the other, so we can write it down t star t, and then you can take this before. So this is c t star minus c bar t, and 1 minute. I think so c t star t into c bar I, yes, Mr. T, yes. So this is I am taking before, this I am taking later, and then c bar of I. Okay, now what does that mean? That means you can take t star common here, and that will gives you t star of so that will gives you, okay, t star of t minus ci, okay, t minus ci, and from here you can take common c bar I. If I take common, then I have t minus ci. Okay, is that clear? So c bar I take common, then t minus ci will be here, and then it will be, so I star equal to identity again, so it will be t star minus c bar I into t minus ci, which is nothing but t minus c bar I whole star and t minus ci. Okay, so that is the proof. So this is the proof that t minus ci is normal operator. Okay, so now the next property tells you that whenever we choose any eigenvector of t, so that eigenvector will be also eigenvector of the t star. See, in general it is not true. In general, if t is a normal operator, then as it is a suppose t is a operator whose adjoint exists, you don't know that it's normal or not, then the eigenvector of t is may not be equal to eigenvector of t star. Okay, so if you choose a eigenvector, so v is an eigenvector of t, then v is also an eigenvector of t star. In fact, you can say something more. You can say that further, or not further, you can say, in fact, you can say that suppose C is the eigenvalue corresponding to the eigenvector V, then you can say that TV equal to, if TV equal to CV, this implies T star V equal to C bar V. Okay. So what is the assumption? I'm assuming that T is actually a non-operator, and in that case, every eigenvector of T is also eigenvector of T star corresponding to the eigenvalue which is actually conjugate of the original eigenvalue. Okay. So how do you prove this thing? So the proof needs some trick, not so much trick. So let me just use this thing. So you start with that. So let T of V equal to CV, because V is eigenvector, so V is obviously non-zero, and there exists a C such that TV equal to CV. Okay. So then what you can do, so you can actually define another operator. Say let me write down, say T dash. So what is my T dash? T dash is equal to T minus C of I. Okay, so this is actually, you can write down T minus Ci of V equal to 0, right? So V is in the null space of T minus Ci, and this operator I am defining now, T dash. Now what is the advantage of T dash? Now you see that T dash of this V equal to 0, okay, first of all, and also T dash is normal. The property number 2 we prove, right? Normal. Okay, so this two property immediately you can say. And now we will use the fact that the property 1 tells you that T dash of V, actually the norm, which is equal to the T dash star of V. Okay, because they have the same norm, but T dash of V is nothing but 0, right? Because T dash V is 0, so norm of a 0 element is always 0. So on the one hand it is 0, on the other hand this is, you can write down T star, so T dash, okay, so let me maybe add one more step. So T dash equal to T minus Ci, and then whole star of V, this norm, right? But this is again T star minus C bar I of V norm. Okay, now norm of this is 0 means what? So that means that this is norm of T star V minus C bar V equal to 0, and norm of some vector is 0 means this implies T star V minus C bar V has to be a 0 vector, and hence T star V equal to C bar of V. Okay, that what do you want? So that proves that V is also an eigenvector corresponding to the eigenvalue C bar, okay, of T star. Okay, so this is the proof. Okay, so what we prove? We prove that whenever you have normal operator, then the eigenvectors of each of the normal operator t are also eigenvectors of t star, but the eigenvalues are not the same. They are complex conjugate of the original eigenvalue. But if it is a real vector space, obviously then both are same. Okay. Okay, so this was also very important property, and then another property we would like to discuss, that is also one of the very important property. Now you recall that whenever you have in general vector space, whenever you have two distinct eigenvalues, then you want to know what about the relationship between the eigenvectors corresponding to the distinct eigenvalues, and we proved that those eigenvectors must be linearly independent, right? But if you have a normal operator, then you are getting more, not only linearly independent, you are getting something called orthogonal. So you have more information. So how do I write down? So eigenvectors of t corresponding to the distinct values are actually orthogonal. Okay. T is normal is given. Okay, so it's not true for in general operator. Okay, so T is so read T is a normal operator. Okay, so eigenvector of a normal operator corresponding to distinct eigenvalues to the distinct eigenvalues are orthogonal. Okay, so the proof also so let me just give the idea, maybe full proof. Okay, so start with two distinct eigenvalues. So let some C1, C2 be two distinct eigenvalues of t corresponding to the eigenvectors say v1, v2. Okay, so what does that mean? Then v1, v2 cannot be 0, and also t v1 equal to c1 v1 and t v2 equal to c2 v2. Okay, and with the fact that v1 cannot be 0 and v2 cannot be 0. This is the thing is given to us. Now we will claim that these v1 and v2 are actually orthogonal. Okay, so how do you prove? So we'll start with this inner product with v1 and v2, and we will show that this inner product must be 0. So what we'll do, we'll just multiply by c1 here. So what will be this? C1 v1 will be, you can write down that by inner product property c1 v1 inner product with v2, but c1 v1 is nothing but in t v1, right? But because t is not t has adjoint exists, so you can write it down as v1 comma t star v2. Okay, but t star v2 is nothing but so t star is the adjoint of t, and t is normal, and hence you know that this t2 v2, that implies t star v2 equal to c2 bar v2, right? That we just prove it. We can write it down here, c2 bar v2, right? But then c2 will come outside, so it will be c2 bar whole bar, that is c2, and v1 v2. Okay, so that's what you have. You have C1 minus C2 into inner product with V1 V2 that equal to 0, right? But C1 C2 are distinct, as C1 not equal to C2 distinct, so this implies the inner product must be 0. So the inner product with V1 V2 is 0. Okay, so this is the proof. So that means V1 V2 are orthogonal to each other. So in general, what do you know for vector space? Okay, that eigenvectors corresponding to distinct eigenvalues must be linearly independent, right? But it is more things true when you have normal operators. So in case normal operators, corresponding eigenvectors of distinct eigenvalues are actually orthogonal to each other. Okay, so these properties are very important properties. Okay, and now what we would like to tell that the theorem which we proved on last day actually for fine. I mean in the beginning, okay, I said that okay, so if we find dimensional comprehensible space, then the normality is actually equivalent to saying the existence of orthonormal basis of eigenvectors, right? But this theorem is actually you need actually fine dimensional things property, and also you need it's computational obviously. So the both are important. So first of all, you can talk about fine dimensionality is important because you can actually show that there are examples that when you have infinite dimensional in a block space and you have you can define the operator which are actually normal, which is a normal operator. Okay, so that means that this star exists and they come with each other. Okay, but the problem is that even T and T star exist, the operator that linear vector space, the T may not have even a linear eigenvectors. There may not exist eigenvectors. Okay, and this kind of example are there are many such examples are there. Okay, so find out what is the example. Okay, so now now the question is that can we actually or maybe I can just give some hints for that, so, and you can do it. Okay, so let me give some hints for this. So suppose my vector space B is or maybe this is classically people define H, so let me define H here. So what is H? H is this continuous function on 0 to pi, and the inner product is what? So inner product is 0 to 1 by 2 pi 0 to pi fx gx bar dx. This is the inner product with f1g for any two continuous functions on complex field control function on closed interval 0 to 2 pi. Okay, and you choose that one orthonormal set S, which is n belongs to z integers. Okay, what are the fn's are e power I n t. Okay, and your t is actually varying from 0 to 2 pi, and this we already show these are actually orthonormal. These elements are orthonormal elements. So S is a collection of orthonormal set, and you can talk about the vector space spanned by this S. So let my V is actually vector space spanned by this S, right? So that means S will be a orthonormal basis for V. Okay, so S will be orthonormal basis for V. So in this case you can actually define linear operator on V which is normal but not actually that does not satisfy the condition that it has a orthonormal basis of eigenvectors. Okay, so this is though these are orthonormal basis of V, but you cannot find out the basis because elements are eigenvectors of the linear operator. Now how to define linear operator? So that T you are defining from V to V by you taking any operator, any continuous map, and then you are sending to the kind of f1 of f. This multiply. These are complex number. Okay. So what does that mean? That means T of f operator, right? So when you acting on x, it is multiplying f1 of x into t. Okay, so t of x. So what does that mean? That means this is e power I n t, right? N equal to 1 here. So it into f of x. This is the map actually. And then you can easily show that this that adjoint exists, and adjoint will be of this form. It sends t of f to t of f1, f minus 1 of f. This will be the adjoint. You can show that. It's a homework, okay? And not only that, you can also that t star commutes because t star is identity operators. Okay. So they commute each other. Okay, so that means t is normal, right? T is normal. Okay, so I did not define something else, but otherwise it has more property that we will define later. Okay, so t is normal, but one can easily show that t doesn't have a eigenvector. So that t does not have any eigenvectors. Okay, this is homework. And obviously you can show that the existence of eigenvector will contradict the fact that the set S is actually orthonormal. I mean, they are linearly independent. Orthonormal is more than linearly independent. But if there is an eigenvector, then you can put that the set S become a dependent set, linearly independent set. That is a contradiction. Now, so you can see that this is even if we choose that this is a map, a real value function, still the same problem will happen. Okay, so even if we choose that this is real value function, and if we define the map from fx gx only, still the same problem will occur. Okay, so now how to solve this kind of issues, like where you can say about that whenever in a product space. Okay, so that means the normality property is actually not sufficient to say that you always have a basis which is actually orthonormal and also contains the eigenvectors of some certain operator, right? But then what more you require, and this condition is called, actually there is something called Hermitian. So I'm not going to define that. Okay, so definition. So let P be an inner product space and T belongs to LV. Okay, and then we say T is Hermitian or self-adjoint okay. If what happens, so you can understand self-adjoint. So what does that mean? That means T and T star are equal. Okay, so whenever in a product space, so you're defining that those operators which are actually they are same with their conjugates, adjoints, and this operator are called cell adjoint operator or Hermitian operator, right? And also similarly you can define for matrix. You can define a matrix for Hermitian matrix, Hermitian or cell adjoint, whatever matrix. If what happens if that matrix A is actually same as A star. A star is complex conjugate, okay, conjugate transpose. So you take the complex conjugate of the element and then take the transpose. In that case, it's called Hermitian matrix. Okay. And the obvious fact is that from here that if that vector space V is actually real in a product space, then what happens? Then it is actually cell adjoint is nothing but equivalent to symmetric, right? So because A star will become A transpose, so A equal to A transpose become, okay, so note that for the case of real inner product space, this cell adjoint is equal to cell adjoint. So cell adjoint is actually equal to what is called symmetric. Okay, so symmetry operator or symmetric matrix or whatever. Okay. So what does that mean? That means so maybe I did not define it for symmetric operator. So symmetric operator means the matrix representation of that operator. So is that symmetric matrix, right? Okay. So one part is so there are one more observation from here. So if we have a basis which is orthogonal basis, then obviously with the orthogonal basis of the vector space V, then T is cell adjoint. If and only what happens, then the matrix representation of that is actually cell adjoint matrix. That is the meaning of the relation between the operator T and the matrix corresponding to a orthogonal basis. Okay, so now maybe we will define some of the properties of these cell adjoint operators, and let's see what happens. So properties. So let T belongs to LV be a self or Hermitian operator. Yeah, Hermitian operator, and you just assume more. You assume that the dimension of V is finite. Okay, for infinite it is not true in general. Okay, then what happened? So then actually property is that these eigenvalues, whatever we discussed so far, they are real actually. So eigenvalues of T are reals. Okay, that means you choose any eigenvalue, that must be real number. Okay, and the proof is what? So this is first property. Let me give the proof. So what is the proof? Proof is that you know that so let me start with that. So let C be an eigenvalue of T and V be an eigenvector corresponding to C. vectors of T corresponding to C okay. Then what happens? Then obviously you know that TV equal to CV first. That's the basic identity, and then and obviously B not equal to 0. It's eigenvector, right? And now you can say more. So you know that T is self-adjoint. So as T is Hermitian, so we know that T and T star is same. So TV equal to T star of V. Okay, but TV equal to is nothing but CV. But T star is V, nothing but C bar of V. That we know that for normal operator this is true, but self-adjoint, okay, so this is, you just take a note that this self-adjoint are normal, okay. So self-adjoint are also normal operator, right? Normal operators, because T and T got T star, right? So T star will be T square will be T star T same, right? So T star will be equal to T square, that will be equal to T star T. So they come with each other. And for normal operator, you know that T star of V equal to C bar V, right? And that tells you that C minus C bar of V equal to 0, but B not equal to 0 implies C equal to C bar, right? So C equal to C bar means, so C is real, so thus C is a real number. C belongs to R. Okay, so eigenvalues are all reals for self-adjoint operators. It is not true for that normal operators or other operators. But when you have a self-adjoint operator, then eigenvalue must be real number. Okay, this is one. And second thing is that, so if you start with this real inner product space other than complex, then the coefficients polynomial actually split. So what does that mean? That means split over R. Okay. So if V, so V such that dimension of V is finite and if is R real vector space or any subspace of real vector space, so then what happens? Then the characteristics polynomial of any Hermitian operator C1 operator split means split over R. Okay, and this is almost obvious, because we know that when you have a Hermitian operators, then their eigenvalues are always real, right? And now if eigenvalues are real, and then what you can say? You can say that, okay, so maybe let me write down proper proof. Okay, so V final dimension is given. So what does that mean? That means you can find out an orthonormal basis of V, right? Always. So let the B an orthonormal basis of vector space B, because vector space is finite dimensional. So you can use Gram-Schmidt method to find out an orthonormal basis of V, right? And they find out what is the matrix representation of T. So T is an Hermitian operator. This is given. So T equal to this is given. Okay. And T with respect to B is that maybe the matrix A. Okay. And so obviously that means A equal to A star, right? That is the meaning of Hermitian. This is this. Okay. So this is we know. So now corresponding to A, you can define. Okay, so A is a linear operator, and you can now what you can do. So my original inner product space is over R actually. So what I can do, I can write it down a map from this A is a in cross-n matrix, right? So I can define a map from like this. So for A, the matrix A, what you can do, you can define a map, so TA, which is from Cn to Cn. For complex, I am writing complex inner product. So this is over C. I am doing it, okay. So how do I define? So I am defining you choose any vector V, which is inside Cn, and then defined by AV for all V belongs to Cn. Okay. Now this inner product space Cn over C is over C, right? And C is algebraically closed. What does that mean? That means the characteristic polynomial of T is split, right? Over C. So the characteristics poly of TA split over C, right? So if the characteristic polynomial of C is split over C, and we also know that this matrix representation of this with respect to the basis, standard basis of Cn. Okay, so you choose that maybe beta dash is the standard basis of Cn over C, then it will be that original matrix A, right? Because this is my left multiplication, and A is symmetric, so this TA is also symmetric, right? A is self-adjoint, so T is also self-adjoint, right? And hence also these eigenvalues are real because TA is self-adjoint. Eigenvalues of TAs are reals. Okay, so it is split over C, but eigenvalues are real, so this implies characteristic polynomial splits over R itself, right? Because all are single, like characteristic polynomial is a product of linear factors split, and every element are the roots are nothing but real number, right? So characteristic polynomial of TA split over R, splits over R, real number, right? And done. And now you see the characteristic polynomial of TA is nothing but characteristic polynomial of A, because they are the same matrix, and characteristic polynomial of A is nothing but the characteristic polynomial of T. So characteristic polynomial of T split over R. Over R, right? Done. So for real inner product space and Hermitian operator, the characteristic polynomial always split over R. Okay. So these two properties is going to help us to prove that fundamental theorems for real inner product space. What we did not get for normal operators. So in normal operators, when we have a complex inner product space, then we know that normality is equivalent to existence of orthonormal basis of eigenvector, right? But if you have a orthonormal basis of eigenvector, that does not guarantee that that operator is normal or not, unless you have a complex vector space. Okay. For real vector space, what you have? Real vector space, it is not true that non-operator exists. But what you can say that it is always true that for real vector space, the existence of self-adjoint operator is equivalent to the existence of an orthonormal basis of eigenvectors of that operator. Okay, and then this is the theorem here. Theorem. Okay, so let be a finite dimensional real inner product space. Okay, real, and you have T belongs to LV. Okay, this is given to you. So then you can say that the equivalent condition of Hermitian operator, then T is Hermitian or self-adjoint, whatever. Hermitian if and only if. So this is both the necessary and sufficient condition. Okay, that V has an orthonormal basis consisting of what it consists of eigenvectors of T. Eigenvectors of T. Okay. So it's very interesting that whenever you have a real vector space, then existence of normal orthonormal basis so whenever real vector space, then normality does not imply the normal orthonormal basis of eigenvectors and vice versa. But for the real vector space, you can say that self-adjoint is equivalent to something, and then we need to prove it. So what is given? So it is given that T is self-adjoint which implies that characteristic polynomial, and over obviously R, I am taking real vector space. Okay, characteristics polynomial of T splits over R. Okay, so if the characteristic polynomial of a linear operator split, then you can use now. So thus Schur's theorem, you remember what Schur's theorem tells? Schur's theorem implies existence of an orthonormal basis of V such that what happened? So basis maybe say B such that T with respect to this matrix of T with respect to this basis B. So this is actually upper triangular. Right? So now I have to prove that this basis is actually the elements of this basis are also eigenvectors. Then I am done, right? Orthogonal basis always exists, and which tells you that it is upper triangular. But can you show that these elements of the orthogonal basis are also eigenvectors of T. Let's see whether we can show that or not. Now, because it's upper triangular, then what you can say? You can say that you know that this, suppose A is the matrix which is this, okay, but we know that the operator T and T star are same. I mean, this is cell adjoint, right? So T star is same, so you can write down these, but T star of B is nothing but TB and then whole star, and this is nothing but A star, right? So what does that mean? That means that A and A star are same. That's what I said. So T is upper triangular, the A is upper triangular implies A star is also upper triangular, right? So thus A star is also upper triangular. Now you see that if both the matrices are upper triangular, then what does that mean? That means, so thus A must be diagonal, right? This is the only option, must be diagonal. So it must be a diagonal matrix, right? Now if you have a diagonal matrix with respect to the basis B, and then what happens? Then the basis vectors are nothing but the eigenvectors, right? So that means that T is diagonalizable, and hence the basis vectors are eigenvectors. So this implies that B consists of eigenvectors of T, eigenvectors of T. Okay, what was the theorem? So this is the theorem. So this is the proof. Okay. So whenever you are talking about five-dimensional real linear product space, then you can talk about the existence of orthonormal basis consistent eigenvector equivalent to the saying that the operator is self-adjoint or Hermitian. Okay, clear. But for complex symmetric, so for real, obviously for real inner product space, self-adjoint is nothing but symmetric, right? Real symmetric, whatever, yeah. So in the case of complex symmetric matrix, this is not true actually. So we can give an example here. Okay. So so you choose a matrix A, which is maybe of the form, say 1 I. Okay. So this is obviously complex matrix, and you see that this matrix is also symmetric, right? So A transpose equal to A. Now what is the Hermitian? I mean A star. So A star is nothing but, you first take star and then compose. So A1 will be 1, then I will become minus I, and this will become minus I, this is minus I, right? So A star is actually this operator, and now you can easily check what is A star. So A star, okay, so A star is, okay, so let me write down, and I will show that though it is symmetric, but A is not actually normal. Okay, A is not normal. So what I am proving that if you start with real symmetric matrix, so they are self-adjoint, okay, and self-adjoint matrices are normal matrix, okay. So for real number, for complex number it is not true. For complex number, if you start with a complex symmetric matrix, they may not be self-adjoint, and they may be self-adjoint, but they may not be self-adjoint itself. They may not be normal actually. So that is the example I am giving here. So now, so normal means what? That A star must be commutative with A star A. So what is A star? A star will be is 1 I minus I, right? And if you multiply these two things, then you have 1 into 1 1, and I into minus I is minus I square, which is plus 1, so this is 2, and then 1 into minus I is minus I, and minus I into 1 is 1 again, so this is 1 minus I, and this one is what? So this is I minus minus plus 1 plus I, and then last one is what? Last one is I into I square, so minus plus 1, and then I into I minus I square plus 2, so this is 2. And you see that obviously A star A, so this is not normal, right? Okay, so A star, and then you find out A star A and check that A star A is so what is A star A? 1 minus I minus I minus I, and then 1 I. So 1 into 1 1, then this 2, this is 2, and this is I. Okay, so but what is this? So this 1 into I, this is I, and then plus 1 plus I, and then this one is 1 minus I into minus I, and then plus, so this is 1 minus I. Now you can see that these two are not same. Okay, so A is not normal, though A is symmetric, complex symmetry actually, complex symmetric. Okay, so that the theorem tells you that when you have a real symmetric matrix, then only you can say that this is self-adjoint, and the self-adjoint are normal. But in general, if you have complex symmetric matrix, then generally normal. Okay, so I'll stop here.